Okay, so homework 9 is out. Please forgive my broken Japanese. Did Latin on the last homework. I figured I should have another foreign language on this one. Please don't submit your solutions in Japanese. Actually, we do have a PhD student in the department who speaks Japanese, so go ahead. We'll just have Kent grade your homework. You won't mind. I've been started over the weekend grading the midterms. One thing that you might have noticed if you've looked at the midterm solutions on the course website recently is that they include 3 common incorrect solutions. And roughly speaking, the order of popularity of the solutions I've received so far are some version of take the original graph, assign capacities to the edges according to distance from Earth or distance from Fillory or both, and run maximum flow. That's probably the most common solution. The second most common solution is find edge disjoint paths in the original graph, and then for each path figure out how many people can march down it in H hours. Both of these solutions are incorrect, but nonetheless do show some insight into the problem, and so they will be getting some substantial partial credit. What I don't know is whether the following solution may or may not be correct. Okay, and so far I haven't seen anybody submit the solution, but I've seen a couple of people working towards it, and so the people who are working towards it are likely to get even more partial credit. But the third most common answer is the correct answer, the canonical answer that was posted in the solution, where you make H copies or H+1 copies of the graph and redirect the edges the right way. The solution that I don't know whether it's correct or not looks like the following. I am going to take my graph, whatever it looks like. Here's Earth, here's Fillory. I have edges which there's an argument in the homework solutions that shows it doesn't matter whether I assume these are directed edges or undirected edges. So I'm going to make the assumption, and I don't know whether this assumption is correct or not. This is in fact the main issue, that there is an optimal solution of the following form. I find some collection of edge disjoint paths. In this case, I'm not going to be able to find that many. I'll just cheat. I find some collection of edge disjoint paths, and I will send as many people as I can down the red path. I'll send as many people as I can down the green path. I'll send as many people as I can down the purple path. And the overall number of people that I can send down any particular path is H minus the number of edges. Actually, let me just write it the way that several people wrote it. The length of the ith path plus 1. But of course, if this is negative, I can't send anybody down this path. And then I want to sum this up over I. So lots of people suggested something along this line where they said, just compute any collection of edge disjoint paths and report this answer. The problem with that is there's absolutely no reason for those paths to be short. The graph is enormously huge. I might wander from Champaign to Urbana via Los Angeles, and that's a path, and you can flow down it, and max flow might return that, and fine. So on the other hand, if I assume that there is an optimal solution that has this structure, then there are a couple of things I can do. The first thing I can do is I can discard any path whose length is greater than h. I can just ignore it, right? Because any path like that is not going to contribute to the eventual solution. And so if there is a solution that consists of a bunch of edge disjoint paths, then there is an optimal solution that consists of a bunch of edge disjoint paths, each of which has length at most h. And because of that, I can in fact just work with this simpler objective function. Only now I can kind of either assume that the number of paths is going to be equal to the max flow value, or I can do a binary search over, search for the, some other way for the right number of paths. Which means in the objective function that I'm looking at, well, I know what h is and I know what 1 is. The only thing I'm really trying to maximize is minus the sum of the lengths. Or in other words, I'm trying to minimize the sum of the lengths. Okay, so I want to find a maximum collection of edge disjoint paths with minimum total length. And the way that I do that is I assign to each one of these edges a capacity of 1 and a cost of 1. And I run a min-cost max flow algorithm. And this would actually be faster than the canonical solution because the running time of the algorithm doesn't depend on the parameter h. It's purely a function of the number of vertices and edges of the original graph. The correctness of this algorithm boils down to the question, is there always an optimal solution that has this structure where you can identify a set of paths and say, okay, you guys are all going to go down path 1, you guys are all going to go down path 2, you guys are all going to go down path 3. These paths don't share any edges, which among other things means nobody ever has to stall in the middle and wait for somebody else to go through the gate before it can be their turn. If there's an optimal solution that has this structure, then I'm reasonably confident that this algorithm or some slight variant of this algorithm will actually be correct. Now, a couple of people have gotten very close to this by saying, I'm going to find edge disjoint paths, but I'm not going to do it using any old algorithm. I'm going to explicitly use the Edmonds-Karp short pipes algorithm. So the subtlety there is, this is almost right. The problem is that when you're running the short pipes algorithm, you're looking for shortest paths in the residual graph, and you're counting the length of the path in the residual graph as the number of edges. In order to make that correct, you have to count the length of an edge if it's a backwards edge that you introduced because you pushed flow along it as -1 instead of +1. So if you're undoing a walk that you did earlier, Edmonds-Karp would still count that as adding 1 to the length. Whereas what you actually want to optimize for in computing these shortest paths, you would want to count that as a -1 in the length of the path. So this is why I'm leaning at this point for the people who said find the edge disjoint paths using the short pipe heuristics. Like, it's not quite right, but it's really close. Those people are going to get most of the points, even though I'm pretty sure the algorithm's wrong. Okay. One thing I was actually really surprised by, normally when I see a fourth of the class turn in the same incorrect answer, it's because it's a problem that I've given before, it's in the notes, and I assume there was a study group that went and solved the problem and came up with a slightly incorrect answer, but they all remembered it and all had notes on their cheat sheet. This has happened several times before. What happened this time was there was about a fourth of the class who came up with wrong answer number 1, but was showing some insight. A fourth of the class that comes up with wrong answer number 2, showing some different insight, for a problem which I made up for the exam. So I don't know what to think at this point. Lots of people had the same insight and conversely had the same misconception. So my guess is that the moral of the story is this is probably a good problem to put on the homework next year. Okay. So we're still working out exactly what the right thing to do for that is because of this correctness issue, but we are because as expected that was the hardest question on the exam. We're going to be deliberately generous with the partial credit. I'm happy to answer questions now, but it might be easier for that particular question to hold off until after we've actually graded everything. Then I'll have a clearer picture, hopefully on Thursday. Yes?
What if you had some of those insights, but read that incorrect answers would be given any partial credit, so you crossed them out and put I don't know?
Send me an email.
Okay.
If that's what you did, we'll look at your crossed out answers. If you erased the answer and wrote I don't know, then not much we can do. Okay. So starting on Thursday, we started talking about the last chunk of the semester, talking about how to prove that problems are hard, and later in the semester, what to do about them if they are. And I introduced, or reintroduced for people who were in 374, this notion of NP hardness. And roughly speaking, being NP hard is a statement about a problem's relationship between two large classes of problems, which intuitively, at least, you can describe as follows. P is the set of questions that you can answer in polynomial time from scratch. Here is a graph. Does its minimum spanning tree have weight at most 1,000? Right. NP is up to some subtleties about yeses versus nos, which are important, but maybe not so important for this class. NP is the set of problems where if you're given the answer and given a proof that that answer is correct, you can verify that in fact that is a proof in polynomial time. So P is the set of exams that you can take in half an hour, and NP is the set of exams whose solutions you can read in half an hour and understand and believe. Okay. So a problem is NP hard means that if X belongs to this set P, if X is a problem where any instance can be solved in time polynomial in the size of that instance, then P equals NP. Okay, so this is a conditional statement as the definition of something being NP hard. From the sort of point of view of physical laws based on experiential evidence, we don't believe that this is true. And so this statement, if X is in P, then false, is logically equivalent to, X is not, there is no polynomial time algorithm for P. Now, this is formally intuition, but for purposes of this class, it's the right intuition to have. What we're trying to do when we prove that something is NP hard is we're trying to show there is no fast algorithm that will always exactly solve every instance of the problem in polynomial time. On the other hand, it's a little bit difficult to talk about sort of, reason about a problem and do it in terms of these sets, these infinite classes of infinite sets of strings. Fortunately, Steve Cook and Leonid Levin have already done this. So there's this lovely theorem by Cook and Levin that says circuit sat is NP hard. So if you recall, circuit sat is the problem whose input is a Boolean circuit, a DAG whose vertices are AND gates, OR gates, and NOT gates, except for input vertices on one side that are all sources, and a single output vertex on the other end, which is a sink. And the question is whether one can assign values to the inputs such that when you evaluate the circuit, the value that comes out at the output is 1. Or alternatively, no matter what values you put in at the input, the output is always going to be 0. Okay. Now, from this, last time we proved that SAT is NP hard, where SAT is the same problem, but instead of being given a graph that describes a set of wires and gates, you're just given a formula, a statement in the algebra of Boolean variables. So you have variables that are connected by operators like and or and if and only if and not. And the question is whether there is an assignment of values to the variables. A is true, B is false, C is true, and so on. So that the entire expression evaluates to true, or is it the case that no matter what I assign to the variables, this expression is always going to evaluate to false? And then at the end, we showed an argument which is ultimately due to Richard Karp, who really was the person who took Cook and Levin's result, or as he knew it at the time, Cook's result, and leveraged it into showed that you can take the existence of a natural NP hard problem and use it to derive literally thousands of other NP hard, showing literally thousands of other problems for NP hard. And the first problem that Karp in the early 1970s considered was this special case of SAT called Freesat, where the typical input for Freesat, it's a Boolean formula, but it's one that has a very special structure. So you have clauses which are ANDed together, where each clause consists of three so-called literals, which are ORed together, and each literal is either a variable or the negation of a variable. Okay? So this is called a clause. This or this, these are called literals. And the letters themselves are variables. Right? And again, the question is whether there is a way to assign Boolean values to these variables so that the entire expression evaluates to true, or is it the case that no matter what values I assign to A, B, C, and D, that I'm always going to get false. Okay. Now, this implication is non-trivial because we're trying to prove the non-existence of an efficient algorithm. If we had an efficient algorithm for SAT, it would immediately imply an efficient algorithm for Freesat because it's just a special case. This is like saying, I have an algorithm that can sort any array, and I say, well, but can it sort an array when the length is prime? Of course it can. That's a restriction on the input, but the more general algorithm is correct for all arrays. Here, what the one possibility is, we can't necessarily check whether arbitrary Boolean formulas are satisfiable in polynomial time, but maybe if the formula has some special structure, then we can. And so Freesat is not quite the simplest structure where we can show that, no, even if the input obeys this very restricted form, it's still NP hard to decide whether the formula is satisfiable or not. Okay. Now, the way that both of these arrows worked is by doing a reduction argument. Okay, this is the way that we prove that things are NP hard, except for the Cook-Levin result, which relies on much more formal definitions of what it means to be in P and NP, and ultimately goes down to the level of Turing machines. We're not going to need to think about Turing machines when we're doing NP hardness proofs here. But the way that we want to prove that some problem X is NP hard, the idea is that we need to choose some known NP hard problem Y, and then for the sake of contradiction, I'm going to assume that there is a polynomial time algorithm for X, and I'm going to use that to build a polynomial time algorithm for Y. Okay, so I'm going to assume for the sake of argument that there's a polynomial time algorithm for X. Of course, this doesn't exist. But for the sake of argument, we assume that it does. And now I'm going to describe an algorithm to solve Y in polynomial time using this supposed polynomial time algorithm for X as a subroutine. So this is a proof by contradiction. Assume that there is a fast algorithm for X, prove that there is a fast algorithm for Y, even though Y is NP hard. That's silly. You can't have a polynomial time algorithm for something as NP hard. X must be hard as well. My assumption that this polynomial time algorithm exists must be false. And so far, the reductions that we've seen from circuit SAT to SAT and then to Freesat have largely been of the form of let's change notation. From circuit SAT to SAT, it's just a question of the realization is that hardware and software are essentially equivalent. You can take a circuit and write it down in algebraic notation. And conversely, you can take a formula and implement it as a circuit. So in fact, I could, in this particular case, if I wanted to, I could drive that first reduction backwards. I could have started with just sat. When I went from sat to 3sat, I had to do a more complicated transformation that involved introducing some new variables. But at all times, the formula that I was, the structure that I was playing with and manipulating was a Boolean formula. And the question was, is this Boolean formula sometimes true or is it always false? What I want to talk about today are problems where we step away from this question about logic, which is a little bit too close to what we think of as general computation, and think about even more specialized problems. Again, all the reductions I'm going to talk about today are due to CARP, that show, some of the power of this theory and some of the generalities of what we can show. Okay? So I'm going to start by considering the following problem. Maximum independent set. Okay, so the problem is that I'm given a graph, got some vertices and I've got some edges. And in this graph, an independent set is a collection of vertices that do not have any edges in common. Okay, so the goal is I want to choose as many vertices as possible so that no edge has both endpoints chosen. Okay. Once I've covered the edge, I can't choose the other endpoint. So no two vertices that I've chosen are neighbors. All right. Now, normally, what one does in an algorithms class when you see a problem for the first time is you start thinking about how to solve it. Don't do that. Don't do that yet, right? Okay, so the input is a graph, an undirected graph, just to be clear, G, and the output is the maximum number, let's say the maximum size of an independent subset of vertices. One of the things you'll notice here is that I'm asking about, can you return the number of vertices in the largest independent set? And you might wonder if that actually makes a difference, whether I think about just computing the size of the largest independent set, or if I actually want to compute the largest independent set. This is very much in the same flavor as like dynamic programming algorithms, where do I want to compute the edit distance, or do I actually want to compute the sequence of operations that achieves the edit distance? It really doesn't matter. One can show that if you had a polynomial time algorithm that computes the maximum size of an independent set, you can use that as a subroutine to compute the actual maximum independent set in polynomial time. Obviously, the other direction works as well. If you can give me the largest independent set, I can count. Okay. So, but for purposes of NP hardness, those two things are equivalent. So we might as well think about what looks like the simpler problem. Okay. So I'm going to prove that this problem is NP hard, and I'm going to do it by describing a reduction from Freesat. And remember what this means. This means I'm going to assume that I have a magical algorithm for maximum independent set, which has, by convention, a rainbow on it. I'll stop at yellow, I think. No, I have to always go red. Okay, there's a rainbow. This is something my 5-year-old would recognize as a rainbow. I'm going to assume that there's a polynomial algorithm for maximum independent set. And using that algorithm as a subroutine, I'm going to build an algorithm to solve Freesat. Now, if I'm building an algorithm to solve Freesat, that means the input to this algorithm has to be a formula, which I'll call phi, and it has to be an arbitrary formula. I know nothing about this formula other than it's in conjective normal form, and it has exactly 3 literals per clause. I cannot assume anything else about that. Okay? And then I need to draw the larger box a little bit bigger here, excuse me. What I need to do is somehow transform this into a graph. This graph is going, the maximum independent set algorithm is going to output some integer k. I need to do some post-processing on that integer k and return either true or false. And if I return true, it must be the case that this 3CNF formula is satisfiable. And if I return false, it must be the case that this 3CNF formula is not satisfiable. Okay. The hard part, not surprisingly, is what do you do here and what do you do here? This is the part of the algorithm that we need to design. Right? The part in here, that's magic, and it doesn't exist anyway. So, again, it's tempting to do this because you're shown a problem that you've never seen before, and you're used to, when you're in algorithms class, immediately jumping in and trying to solve that problem. Don't try to solve that problem. Assume that I have already solved that problem. Or if you don't believe me, I don't know, assume Mark Zuckerberg has already solved that problem. And you just want to use, say, Facebook announces a maximum independent set oracle. Okay, great. Now I'm going to use Facebook's maximum independent set oracle to solve my Freesat instance. It's also really important now to say, I'm going to start with an arbitrary formula because I want this 3SAT algorithm to be correct for any formula. But one thing that's a little bit non-intuitive is that this graph that I get is not going to be an arbitrary graph. I don't have to worry about graphs that my reduction doesn't compute. It's enough to show that for that special case of graphs, I get a hardness result. Okay? So let me describe how the reduction is going to work. And to do that, I'm going to use this formula, where now I'm going to erase all the red stuff because it's just getting in the way. Okay, so here is a formula. I'm just using this as an example because it's a little easier to explain this way than by doing full generality. Okay, so the first thing I'm going to do, given my arbitrary 3CNF formula, is for every single literal, I'm going to create a vertex. And I'm going to connect those vertices into triangles based on each particular clause. So for the first clause, I'm going to create a triangle with vertices labeled A, B, and C. B, C bar, D bar, triangle. A bar, C, D, and A, B, D bar. Okay, so every clause is going to turn into a subgraph in the graph that I'm building. This is one of the sort of general features about NP hardness reductions. This object is sometimes referred to as a gadget or a widget. I'm going to have some piece of the output graph from my reduction that corresponds in some functional way to the semantic pieces of the input. So every clause, I'm going to have a triangle. For every literal, I'm going to have a vertex. But now I need some way of gluing these things together. I'm going to add additional edges between these triangles. But one thing I want to point out immediately is that the size of the largest independent set is definitely going to be less than or equal to the number of clauses. Right? Even before I put in the other edges, the reason for this is that once I've chosen one of these vertices in this triangle to be in my independent set, I can't use any other. So if there are k clauses, the biggest independent set I could hope for is to have one chosen variable, one chosen vertex in each of these triangles. Then the second thing I'm going to do, the other edges that I'm going to put in, is I'm going to add edges between vertices that correspond to contradictory pairs of literals. So here I have a literal, here I have a vertex that corresponds to the literal A. Here I have a vertex that corresponds to the literal A bar. I'm going to put an edge between them. So let's see, here are the A edges, B, B, B. There are no B bars. C bar C, C bar C. Here's. Oh, that's a D bar. Oh, yeah, you're right. Can't read my own handwriting. D bar. Okay. So then that D bar goes to this D bar and to that D bar, and I believe that is everything. Okay, so I'm going to add these new edges that represent, in some sense, inconsistency. And the idea now is I'm going to try to choose a vertex in this triangle that corresponds to a literal which I'm declaring to be true. Okay, so if I want a satisfying assignment for this 3CNF formula, it has to be the case that one of the three literals, at least, in the first clause is true. One of the three literals in the second clause is true. One of the three literals in the third clause is true. One of the three literals in the fourth clause is true. Possibly more than one, but it's enough just to say, oh, you know what, I think A is true. And okay, now the first and the fourth clauses are satisfied. Okay. But I need to choose the true literals in the first clause in a way that's consistent with the true literals in the second clause. So I can't declare for the first clause that C is true, and then in the second clause declare that C is false, because that doesn't make logical sense. So what I'm going to do then is to say, in this first clause, I'm going to declare A to be true, and that rules out declaring A bar to be true in this other clause. And so if I choose, uh-oh. I think I'll have to use my finger here. What? Hang on. Oh, great. It's just not working at all. Yeah, let me charge up my pencil. So I'm going to choose, say, A in this gadget, A in this gadget, C bar in this gadget, and D in that gadget. Then that's a consistent choice of right. So that's those four vertices that I've chosen are an independent set, and they also correspond to a consistent setting of variable values that will make the formula at the top of the screen true. So I've declared that A is true, and I've declared that C bar is true, therefore C is false. I've declared that D is true, and again I've declared that A is true. Yes?
Can you keep the setting of B consistent across clauses?
Okay, how do I keep the setting of B consistent across clauses? I don't. I don't need to. It doesn't matter what B is. If B is true, okay. Formula is still satisfied. B is false. Okay, formula is still satisfied. The way that because of the choices that I've made in choosing these particular vertices, the value of B actually doesn't make any difference. Okay. So the intuition here is that an independent set in this graph G corresponds to a satisfying assignment for the original input formula phi. And I say partial because the independent set doesn't necessarily define a value for every variable. In fact, this particular independent set doesn't define a value for the variable B, but it turns out not to matter. Whether B is true or false, setting A to be true, D to be true, and C to be false makes that expression true. Okay? So that's intuition. I've described the algorithm to you, which is, independent set of size G of size equal to the number of clauses equal to. So if the formula up there is not satisfiable, then there is not going to be a way of always choosing a true literal, which means we're not going to be able to choose one vertex out of each of these triangles without one pair of those vertices being, at least one pair, being connected by one of these red edges. We can't, in the case where we're given an unsatisfiable formula, if we try to choose a large independent set, we're going to derive a contradiction. We're going to be forced into choosing a vertex that's a neighbor of a vertex we've already chosen. So what I really want to claim here, and the claim that implies the correctness of this reduction, is the following. G has an independent set of size k for any integer k, if and only if there is an assignment of values to the variables that satisfies k clauses in phi. And this claim means that in the end what we want to do is we build the graph. That's the first box here. We figured out how to do that. And then the last thing we do is we just say, is k equal to the number of clauses? And if k is equal, we return true, and if k is not equal, we return false. All right, so I need to prove this claim. Right? So far, I've shown you the algorithm. Hopefully, it's clear, by the way, that it runs in polynomial time. Formally, I have to say that. Oh, look, it runs in polynomial time. Everybody see how they would implement this in polynomial time? Brute force. Just do it. Okay. Okay, so I need to prove this. I'm sorry. I don't know whether it's the battery in the pencil is running out. Okay, so how does the proof actually go? So let me start by proving this direction. Suppose G has an independent set of size K. I learned this from my high school calculus teacher. Suppose. You know, it goes along with all the other abbreviations that mathematicians like. Okay, so suppose G has an independent set of size K. Then we can let's say assign values to some of the variables of the formula to make those K literals true. Okay. So given my independent set, I'm going to create an assignment to the variables by just saying I need to make those literals true. Now this assignment is consistent because of these red edges between contradictory literals. Right? The reason that I added those is there's no possible way that I could attempt to make a variable true and attempt to make a variable false, because those two vertices can't be in the same independent set. Okay. So that implies now that I have K clauses, each with at least one true literal, because each of the variables in that independent set is in a different triangle. Right? So each of those K variables in the independent set must belong to a different triangle, so those K literals that I found to set to true, they belong to K different clauses in the formula. And that's the end of the proof. Okay. Now if I want to go the other way, suppose some assignment makes K clauses in this to be true. Okay, I'm going to choose one true literal from each of those clauses. And then I'm going to mark the corresponding vertices in the graph. Those vertices lie in different triangles because I chose the literals from different clauses. And they're going to be independent, again, because the only edges that I add between triangles are between contradictory literals. And I know that the literals I chose aren't contradictory because they're all true. And so this gives me an independent set of K vertices, and I'm done. Okay, so given a large independent set, I can find an assignment that satisfies lots of clauses. Given an assignment that satisfies lots of clauses, I can find a large independent set. So in particular, there is an independent set of size equal to the number of clauses if and only if there's an assignment that satisfies everything. Okay. Questions about this reduction? Yes.
Do you give every variables that are, for example, do you give every a bar?
Yes, I link every instance, every variable that's labeled with a variable A. I connect to every vertex that's labeled with the negated variable A bar. That's what these red edges are. Right, so you can see this A is connected to A bar, this A is connected to A bar, and there's no A or A bar in that other class. Okay? All right. So then let me, sorry, wait. Okay, good. Questions? Yes?
I have a question about the
How many, oh God, sorry.
the proof, the second, like sorry, going the other direction, you said there's a valid assignment. How exactly are we proving that like we aren't violating the edges that we have connected to the classes?
Okay, so the question is, how do we know when we choose these literals and then we mark the corresponding vertices, we don't violate the vertices, we don't mark both ends of one of those red edges. And the answer is those edges that go between the triangles join vertices whose labels contradict each other, A to A bar. So I can't choose them both because I only choose literals that have the value true. And one of those is true and the other one is false. Yeah?
So that the bottom one only works for the specific graphs that we described.
That's correct. But that's all that we need. Remember, we need the algorithm to correctly decide whether an arbitrary 3CNF formula is satisfiable. We don't care whether the black box that we're assuming exists can handle arbitrary graphs. Yeah. I'm sorry? So because I'm choosing a true literal, one literal from each clause, the corresponding vertices, there's one vertex for each of those corresponding K triangles. So there's a triangle for every clause. And really what this is doing is I'm just putting up a dictionary that says vertex, literal, clause, triangle, edges between clause, contradiction. And I'm saying, well, what does it mean to satisfy versus what does it mean to be independent, and observing that it's essentially the same thing. Okay? All right. So let me, sorry, one more. You can, but, I'm sorry? You can do a reduction to Freesat if what you were trying to do is prove that Freesat is NP hard. Then no. You always want to reduce from the problem that you know is hard to the problem you're trying to show is hard.
But since we know Freesat it's NP hard, if that one can be reduced to Freesat and we cannot solve
No, okay, so let me again walk through the logic carefully. So I claim that I can reduce the minimum spanning tree problem to Freesat. Does that say anything about how hard the minimum spanning tree problem is? I can derive a really stupid algorithm for a minimum spanning tree. Okay, that's not the only way to solve minimum spanning tree. I'm not claiming this is the only way to solve Freesat, but it is a way to solve Freesat if that magic MIS box exists. But we know that there's no fast algorithm for Freesat. So the only conclusion is that that magic box in the middle doesn't actually exist. Right? We're always doing a proof by contradiction. So the reductions go backwards from the way we think. A lot of people think the way that I thought for the first several times I saw this.
And
Yeah.
I know that there's definitely
Well, I'm taking P is not equal to NP as an axiom for purposes of discussion. Because I don't have $1 million. So. Okay. Okay. So, hey, look, it's the same thing I just shown. Okay. So, there are a couple of related problems. I want to show you these quickly before I go on to the last thing. Instead of finding the maximum independent set, suppose I want to find the maximum clique. So a clique is a subset of the vertices where every pair is connected. Right, so in this case, the maximum clique would be perhaps these 4 vertices. There's no clique of size 5. How would we prove that maximum clique is NP hard? I'm sorry? Okay, so following the example that we just saw, we could say, assume that there's an algorithm for max clique and use it to solve Freesat. But in fact, now, we can go back to the beginning and say, oh, actually, maximum independent set is NP hard. And so it might be easier to reduce from something else besides Freesat. So, in fact, we might be able to do a reduction from maximum independent set. Right. So I'm gonna take this graph G, and I'm going to transform it into this graph G bar that has exactly the same vertices, but G bar has an edge in exactly the places that G doesn't. I'm not going to draw all of it. So the idea is that every edge is going to turn into a non-edge, and every non-edge is going to turn into an edge. And then if I do that, a clique in G corresponds exactly to an independent set in G bar. Because over here, I said I want every pair of marked vertices to be connected, and over there I said I want every pair of vertices to be disconnected. And so I just change the pairs that are connected into the pairs that are disconnected. Okay. More generally, I can think about any binary relationship at all. I want to choose the largest number of people in this room so that every pair knows each other. Or that every pair doesn't know each other. Or that every pair shares at least 3 letters in their last name. Right? I want to find a large collection of people that all pairwise are related the same way. It's all equivalent to the maximum clique problem or the maximum independent set problem. There's another similar problem, the minimum vertex cover problem. Okay, so in this case, again, I'm given a graph. And now my task is not to find a largest subset of vertices satisfying some property, but rather a smallest subset. So the property that I want is that for every edge, I've chosen at least one of its endpoints. And I've done a really bad job of that. So let me try to do something a little bit. This is an awful graph. Did I get everything? No. Okay, fine. This is a vertex cover. I don't need that one. Okay, this is a vertex cover. So for every edge, at least one of its endpoints is covered by the set. How would I prove that this is NP hard? Right, so instead of complementing the input, I'm going to complement the output. Notice anything about the white vertices in this picture? They're not connected, they're independent. So the complement of a vertex cover is an independent set. Right? So this is just the number of vertices minus the size of the largest independent set. So again, this is a sort of thinly veiled version of a problem that we've already shown as NP hard. And so now I have this other problem, which I get by complementing the output instead of complementing the input, is again NP hard. Okay. So in general, problems of the form, I have a set of things, some of which are related by some pairwise relationship. I either want to choose a largest subset of things that are all related, or I want to choose a smallest subset of things such that every related pair is somehow somebody's chosen. These are both hard. Okay. The last one I want to do, and I'm going to have to refer to the notes or point you to the notes for the specific details of this, is a different graph problem. It's this one. So this is the problem 3-color. So here I'm not deciding whether to choose a subset of the vertices or not choose a subset of the vertices. The idea is I'm given a graph G, and I want to color the vertices with 3 colors so that no edge, let's say so that every edge touches 2 colors. And so again, given some kind of graph like this, I want to color, say, some of the vertices red, and, well, green would be better, wouldn't it? Some of the vertices green, and some of the vertices black. Okay, so this is a legal coloring for this graph. Okay. Now it is true that if I look at all of the red vertices, they're an independent set. And so you might be tempted to say, well, I know, I'll find the largest independent set, and I'll look at the graph that's left, and look, the graph that's left, I can color with only 2 colors because I can figure that out with breadth first search. And so if I could only solve the maximum independent set problem, I could solve this problem in polynomial time, and so I have an NP hardness result. What did I do wrong?
Backwards.
I did the reduction backwards. And secondly, I assumed something greedy would work in the first place. So I did the wrong thing incorrectly. That does not imply that I did a proof. So I need to do the reduction in the right direction. I choose a problem that I know is NP hard, and I solve it using a fictional algorithm for 3-color as a subroutine. So I've got a handful of problems that I could choose from. Circuit sat, formula sat, Freesat, maximum independent set, maximum clique, minimum vertex coverage. Which one of those seems like it would be the right one? I want somebody to come up with the snarkiest answer you can. Freesat, because it has 3 in it. And that's the right answer. It's really disturbing how often that is the right answer. There's a 3 in it. Fine. Let's just use Freesat. So, have any of you played the iOS game Threes? Okay, so there's a paper that's about to come out in a conference this summer that proves that Threes is NP hard. What problem did they start with? Freesat. Okay, so here's how. So I'm going to describe a reduction from Freesat. Freesat because 3. Okay. So this is the way the reduction is going to work. I'm not going to be able to walk through the proof because there's only 5 minutes left. I'm going to have a number of gadgets that enforce various semantics about the arbitrary 3CNF formula that I'm given. All right. So remember, I'm given an arbitrary formula in conjunctive normal form with 3 literals per clause. And I'm going to build a graph G. And I'm going to build the graph G that is 3-colorable if and only if the original formula can be made true. There is an assignment that makes it true. Okay, so I'm going to set up various gadgets that enforce some correspondence in the semantics of the formula and the structure of the graph. The first of these gadgets I'm going to call a truth gadget. And what the truth gadget is going to look like is just a triangle. Now I'm going to label one of these vertices T, one of these vertices F, and one of these vertices I'm going to call X. And now this is always going to be part of the graph G. And now one thing to notice is that if G is 3-colorable, then in any 3-coloring, these 3 vertices have different colors because they're all connected. So without loss of generality, I can name the 3 colors at this point. And I'm going to name the 3 colors true, false, and other. Now, if you like, you can say, oh, well, I'm always going to color the true vertex red, I'm always going to color the F vertex green, and I'm always going to color the X vertex blue, and from now on I'm going to call it red, green, and blue. But at this point I've attached semantics essentially to the names of the colors. The colors themselves now have meaning. Any vertex that's colored the same as this is going to correspond to something true. Any vertex colored the same as that is going to correspond to something false. Anything that's colored X is going to correspond to something that isn't a Boolean value. Okay, so that's a truth gadget. The second thing I need is a variable gadget. And here I'm going to create for every variable, not for every occurrence of every variable in the formula. If the variable has 72 instances of the variable A, I'm only going to create one variable gadget for A. And that variable gadget looks like this. Now, that vertex X is the same vertex X from the truth gadget. It's just easier to draw it separately. And now what this enforces is that in any 3-coloring, either A is colored true and A bar is colored false, or A bar is colored true and A is colored false. In other words, those 2 variables encode a truth value. Those 2 vertices, encode a truth value. And then the last thing is I'm going to define a clause gadget. And this is the part, I'm going to argue here by example. Let's say I have the clause A or B or C. So this is, I'm going to take the corresponding vertices from the corresponding variable gadgets. So in particular, if this is A bar, I'm going to choose the vertex A bar from the variable gadget for A. And I'm going to connect them ultimately to the vertex T from the truth gadget. The way that I'm going to connect these in case you're wondering, I've got the cheat sheet right here, making this up. It's like this. Now, this variable T is colored red. That means that these two must be colored green and blue. I don't know which way. But say, for example, if I colored this vertex blue and this vertex green, well, then I have to sort of back propagate here. Well, if I do a sort of brute force case analysis, there are 8 possible colorings for these 3 vertices. A bar is either true or false, B is either true or false, and C is either true or false. As long as at least one of these 3 vertices is colored true, there is a legal 3 coloring of this gadget. If these 3 variables, these 3 vertices are all colored false, then what happens is the following. These 2 have to be colored not false, but different from each other. So one of them has to be colored true, and one of them has to be colored other. Which means that the tip of this triangle must be colored false. And then again, one of the last 2 vertices there must be colored true, and the other one must be colored other, which means that the front vertex must be colored false. But the front vertex is the vertex true. So we have a contradiction. So putting this all together, what you end up with is now actually identifying the vertices that are really the same. What you have is up at the top, you've got the truth gadget. For each variable, you have a variable gadget. And then a clause gadget for, say, the clause A or B or C consists of this variable, A or B or C, and ultimately this connects back up to true. So this is the clause gadget for A or B or C. And putting all the pieces together as I hoped, one can show that this graph that you get is 3 colorable if and only if the original Freesat formula is satisfiable. And the proof is, if there's a 3 coloring, I can extract the values of the variables from the colors of the variable nodes, and that will give you a satisfying assignment. And if the formula is satisfiable, I can color the variable nodes according to the satisfying assignment and propagate the coloring through the clause gadgets in a consistent way. Sorry, didn't leave myself enough time to actually go through the details of that. But if you have any questions, I'll be here after the rest of the meeting. All right, thank you. Hey.
It's related to problem 2. I have this graph that looks like this.
Hang on just a second.